Parched earth, dry riverbeds, and failing municipal pipes are exposing billions of people to acute water stress. Our ground-based water infrastructure is highly vulnerable. Yet directly above these drought-stricken regions sits a massive, largely untapped reservoir. We are constantly surrounded by an invisible ocean of suspended moisture. To understand the scale, look at this volumetric comparison. The smaller sphere represents all the fresh water currently flowing in Earth's rivers. The massive sphere beside it shows the volume of water held in the atmosphere at any given moment, roughly 37 million billion gallons. The physical challenge we face is that this massive supply is suspended as a vapor. In this gaseous state, it is completely inaccessible for drinking or irrigation. To access it, we have to lower the temperature of the air. There is a specific threshold called the dew point. When air cools to this exact temperature, it can no longer hold the vapor, forcing the moisture to condense into a collectible liquid. If we engineer machines capable of artificially triggering this phase change at a global scale, we can tap into a continuous, drought-proof water supply anywhere on the planet. Triggering this phase change is relatively straightforward in tropical climates, where the ambient air is already heavily saturated with moisture. Standard AWGs use a brute force method. Moist ambient air passes through an electrostatic filter. A compressor-driven evaporator coil then chills the air below its dew point, forming droplets. Finally, multi-stage filters and an ozone generator make the water drinkable. The limitation of this brute force method is energy consumption. Chilling large volumes of air requires significant electrical power, averaging 200 to 300 watts per liter of water produced. Furthermore, as the relative humidity drops, the energy required spikes. When ambient humidity falls below 30%, standard AWGs become highly inefficient, practically halting production. Traditional condensation technology provides vital disaster relief in humid zones, but it fails to operate effectively in the arid regions that need fresh water the most. This brings us to the ultimate geographic challenge: extreme desert climates, where relative humidity routinely drops as low as 10%. Harvesting water at these extremes requires highly porous crystalline structures, known as metal organic frameworks, or MOFs. Microscopically, these structures function like molecular sponges. This schematic shows the diurnal cycle. At night, the porous MOF layer passively grabs water molecules from cold desert air. During the day, solar heat forces the MOF to release water vapor, which condenses into a collector, all without moving parts. This process has been proven in the field. These time-stamped photos document a field test in the Mojave Desert, tracking the physical progression of droplets forming on a condenser plate over 3.5 hours. MOFs demonstrate that by replacing electrical brute force with passive molecular chemistry, we can extract liquid water from the driest air on Earth. Moving beyond the microscopic chemistry, atmospheric water generation has broad implications for global infrastructure. It offers a path to complete grid independence. Centralized municipal water systems are highly vulnerable to pipe corrosion, contamination events, and natural disasters. Generating water exactly where it is consumed removes these failure points. The technology scales to meet different demands. While there are small residential units, manufacturers are also building heavy-duty commercial systems capable of producing up to 10,000 liters a day for large-scale disaster relief. By pulling moisture directly from the air, this technology transitions drinking water from a fragile, centralized utility into a secure, decentralized asset. There are still commercial hurdles to overcome. Early MOF structures relied on zirconium, an extremely expensive metal that made large-scale production financially impractical. Researchers are rapidly addressing this with material innovations, replacing zirconium with aluminum. This substitution is roughly 100 times cheaper, significantly lowering the cost barrier for mass manufacturing. Manufacturers are now combining these advanced materials with renewable solar power and battery storage. The goal is to deploy entirely off-grid, cost-effective water farms that require no external infrastructure. As changing climate patterns continue to deplete ground-level infrastructure, tapping into the atmosphere's invisible reservoir remains a critical frontier for securing human water needs.